So previously, we've been able to take derivatives of polynomials, things that had exponents, whether they were integer exponents, things that contained rational exponents, things that involved trig functions, things that were products, quotients, other trig functions. Also, with that's also composite, but composite functions, where we had to use the chain rule. So, in the front of your book, there's this little tear out. In the derivatives that we've done so far, basically the first 8, which just remind you, well, how do you take the derivative of a constant? How do you take the derivative if you've got 2 functions added together? How do you take the derivative of products, quotients, things to a power? Then skip on down to like 13, and you have derivatives of the trig function: sine, cosine, tangent, secant, cosecant, cotangent. So any combinations of those we've been able to do up until this point. So in 5.1, we introduce taking the derivative of natural log. And the derivative of natural log is just 1 over x. More generically speaking, though, because just like when we take the derivative of sine, the derivative of cosine, etc., it's often more than just natural log x. Sometimes we have natural log of x squared plus 1, or natural log of something that's more complicated. So, in general, if we have natural log u, we want to take the derivative of that. The derivative is u prime over u. So, for example, if we want to take the derivative of natural log of x squared plus 1, whatever natural log of goes in our denominator, so we're taking the natural log of x squared plus 1. The derivative of that goes on top. So what's the derivative of x squared plus 1? 2x. So that would be our derivative. I'm going to ask a seemingly stupid question. Do we need a plus c there? We're not integrating. Remember, plus when we do the plus c, when we do an indefinite integral derivatives, we don't have those plus c. So let's do that one. What is our u? U, that's just whatever we're taking the natural log of. So when we take that derivative, the derivative is u prime over u. So u is the sine x, that's what goes on bottom. What's the derivative of sine? Cosine. So y prime is cosine over sine. Or what's another way of simplifying cosine over sine? Cotangent. So if you can remember u prime over u, You can take the derivative of natural log. See if we can find a good one. Ooh, I like this one. Depending on how you look at this, you can make this as easy as you want or as hard as you want. Basically, we have natural log of something. So let's just come over on the side. Our main u is natural log x squared. So you could think about this. We have y is natural log of u. So if we want the derivative of that, the derivative of natural log is u prime over u. So this is u. We need the derivative of that to finish our derivative. Well, if we take the derivative of this, what's the derivative of that? Right. To take the derivative of this, that's the derivative of natural log. This part goes on bottom. The derivative of that goes on top. So it's basically the chain rule. We did the derivative of the outside, which involves derivative of the inside over the inside. So that when we take that derivative of the inside, notice that simplifies. An x on top reduces with an x on bottom. So y prime is u prime over u. We want to simplify that because that's a complex fraction. So if we think as the denominator over 1, multiply by the reciprocal of what's on bottom. So the derivative is 2 over x natural log x squared. So one of the biggest pieces of this is just using good notation. We've discussed in the past when doing things that involve the chain rule, a lot of those we can do pretty much directly, writing down like u prime over u. But if our u prime also involves a derivative, sometimes it's better to go over on the side and make some notes. Okay, our u is that. We need the derivative of that. Well, what's the derivative of that? So when we get our derivative, it's going to be u prime over u. Then we go back and substitute in u prime and u, instead of trying to do all of that in our head in one step. The farther you get in school, the more information you're going to have up there in your head, and the less room there is going to be to just do all of this in your head. The better organized you are and the more things you do on paper, the less likely you are to mix things up. If we take our derivative as it's written, then that would be u. So when we take the derivative, we would be taking also the derivative of that, and we would have to use the quotient rule. Well, you can do that if you want to. There's nothing wrong with that. But remember, with logs, natural logs, there are special rules to simplify expressions. One rule you might remember is if you have log of the quotient, we can rewrite that as the log of the numerator minus the log of the denominator. If we have log of a product, we can write that as log of the first factor plus log of the second factor. If we have log of something to a power, we can bring that exponent out front. So while, yes, we can take the derivative of this function in its present form, that's going to get really messy when you start having to deal with that quotient. So before we take the derivative, let's rewrite the right side. We have a quotient, so let's rewrite that as natural log of the numerator minus natural log of the denominator. That derivative is not too bad. We have two different terms. Both of those are natural logs, so each of those are going to involve a u prime over u. So for our derivative of this first part, what goes on bottom when we take this derivative? X squared minus 3. The derivative of that goes on top, so what goes on top? 2x. Minus, when we take the derivative of this is our u, so that goes on bottom. What's the derivative of this? 1. That goes on top. So that's our derivative. Of course, you could combine fractions there by getting a common denominator. But that is derivative. All right. So with that piece of information there, there are times that we use properties of logarithms to make complicated derivatives a little less complicated. Now, this one is going to be pretty much equally complicated either way. But if we use this same technique that we're about to use, if we had a function, let's say, and in fact, we'll do this one instead. If we had that function and we wanted to take the derivative, yeah, that'd be fine. You have a quotient. You have a product in the numerator, a product in the denominator. So if we took the derivative without doing anything to it, you'd have to use the quotient rule and the product rule twice. Now you could multiply the numerator out and the denominator out so that you use the quotient rule and don't really have a product rule, but it's still not something that's just extremely exciting to do. But by utilizing properties of logarithms, one thing that we've done in the past is we saw, okay, if we take the natural log of both sides, we maintain equivalence. If we do the same operation to both sides, we are still equivalent. Now at this point, we've not taken a derivative. We just took natural log of both sides. That would be like multiplying both sides by 7 or adding 4 to both sides. We just did an equivalent operation on both sides. Now, the good thing about this is on the right side, we have products and quotients. And from pre-cal, we have natural log of various factors. All the factors that are in the numerator, those are positive logs of whatever those factors are. All of the factors that are in the denominator, those are minus natural logs. So natural log of each factor, natural log of x minus 2, natural log of x plus 3, natural log of x plus 5, natural log of x minus 9. The ones on the numerator, those terms are positive. The ones on the bottom are negative. Now, everything that we have here is a fairly simple derivative. So we can take the derivative of both sides. On the left side, what is the derivative of natural log y if our variable of our derivative is x? Yes. So this goes on bottom. The derivative of that goes on top. So the derivative of y with respect to x, we can call that dy over dx. Or you could call it y prime. We'll go with dy over dx. On the right side, we have 4 different terms. We take the derivative of each one. The derivative of that first term, our u is x minus 2. What's the derivative of x minus 2? 1. Our u is x plus 3 on the next one. The derivative of x plus 3. X plus 5 on bottom for the next one. 1 on top. X minus 9 on bottom. 1 on top. Now what we're looking for is y prime, or dy over dx. So how do we get dy over dx by itself? Right. We want to multiply both sides by y. When we multiply the left side by y, y on bottom, y on top cancel, leaving us dy over dx. On the right side, we have all of that. Is that a miniature wolf just walked by the door? Window. Y'all see that? It was actually a dog, but it looked like a miniature wolf. That's got to be some kind of Indian omen. Wolf walks by the door window during class or something. Oh, pen, why are you not working? All right. Well, normally when we have a derivative, if we can have just one variable on the other side, that's what we want. Well, do we know what y is? Yeah. Y is this. That's what y is. So instead of calling it y, we're going to call it x minus 2 times x plus 3 over x plus 5 times x minus 9. That's our derivative. We didn't have to do a product. We didn't have to do a quotient. We took a little bit more time with algebra, but I guess it just depends on what you'd rather do. Would you rather spend a little bit of time making things easier so that when we take the derivative, it's just a straightforward derivative, or would you just rather go ahead and jump in there, not have to do any extra steps, but have a more complicated derivative? Any questions about that one? Doesn't make any sense whatsoever. This is yes, this is no. All right, let's do an implicit derivative. Let's do x squared plus 3 natural log x equals x natural log y plus y. Let's not do that. Plus natural log we want to find dy over dx. So when we take our derivative, what are we taking our derivative with respect to? X. Yeah. That dx on bottom, that tells us that's what we're using to take our derivative. So both sides, we're taking the derivative with respect to x. Now the left side is not that bad. It's fairly straightforward. We have two terms on the left side. Both of those, our variables match. So what's the derivative of x squared? That's just the basic power rule, 2x. The derivative of 3 natural log x, 3 is a multiplicative constant. What's the derivative of natural log x? Sure, 1 over x. Well, what about x natural log y? What's the rule that we're going to have to use to take that derivative? Product. We have something with a variable times something with a variable. So let me come over on the next page for a second. When we take that derivative, if we were to call that u and that v, our derivative is u prime. So what's the derivative of the first part? The derivative of that is 1 times v plus u times v prime. Well, what's the derivative of natural log y? This goes on bottom. The derivative of that goes on top. So that's the derivative of that. This is the product rule. Now we need to take the derivative of that right piece, natural log xy. Well, let's come over on another page and take that derivative. The derivative natural log xy. Now there's more than one way to do this. Any suggestions? That would be the best thing to do. We have natural log of a product. So before we actually apply the derivative, let's write that as two different logs. Natural log of the first factor plus natural log of the second one. We could go ahead and do u prime over u right here, put xy on bottom and the derivative on top, but to take the derivative of this, that's a product that is also going to involve an implicit derivative because we have two different variables. But if we break that up, the derivative of natural log x is what? X goes on bottom, its derivative on top. The derivative of natural log y goes on bottom, its derivative on top. Since the variables don't match, what goes on top then? dy or dx. So that's the derivative of that last term. So just a nice little derivative. Let's rewrite this just a little bit before we solve for dy over dx. The first term, well, 2x, that's about as easy as we can write that. The second term, we can write that 3 times 1, so 3 over x. On the right side, natural log y. Since dy over dx is what we're trying to isolate eventually, let's rewrite this. Let's group the x and the y together. dy over dx over 1, or we could just call that dy over dx. That makes sense what we did there. Well, here we have a fraction that's multiplied. Multiplication is commutative, so we can swap the 1 and the y. So we have a x over y here, a 1 here, well, anything over 1 is itself. Here, we have a 1 over x. We could leave this like this, or we could pull the y out front as a y on bottom, 1 on top, dy over dx. By pulling the dy over dx out of the fraction, that just makes it a little bit easier when we start factoring here. Let's see, we want to get dy over dx by itself eventually, so what should we do next? Yeah, get all the dy over dx on one side. Now, we look at it, these are the only two terms that have dy over dx in them. So let's move everything else to the left side, leave dy over dx on the right side. So that means we want to take natural log of y away from both sides. Take 1 over x away from both sides. So on the right side, natural log y's cancel, 1 over x's cancel, leaving x over y times dy dx plus 1 over y times dy over dx. On the left side, we have a 2x We have a 3x minus 1 over x. Aren't those like terms? Yeah. They have the same denominator. 3 minus 1, that's really close to 2x, 2 over x. So that takes care of that one, those two. Then we have a minus natural log y. Now that we have all of the dy over dx terms by themselves on the right side, what do we do? Factor out the dy over dx. So that leaves us x over y in the first term, 1 over y in the second term. Those have the same denominator, so we could combine those. Y on bottom, x plus 1 on top. How do we get dy over dx? Sure. The opposite of multiplying is to divide, so divide both sides. So the right side, those cancel. The left side, we have 2x plus 2 over x minus natural log of y. Dividing by a fraction, that's like multiplying by the reciprocal. So the reciprocal, y over x plus 1. So after killing a couple rainforests, we come out with that as the derivative. So we didn't necessarily have to do that by logarithmic differentiation. Oh, I'm sorry, that was a different, sorry, my brain is, it's Monday, isn't it? The previous one we didn't have to. This one we did have to do implicit differentiation because we have a mixture of different variables, x's and y's, x's and y's. All right. And that's pretty much section 1, 5.1. Let's take about a 5-10 minute break, and then we'll look at section 2.